Hello, this is Dr. Hanaa Assil, and this video will be talking about the types of reactions. This is mainly for the IGCSE chemistry course. So, the first type of reaction is the oxidation-reduction reaction. You should realize that you should know definitions of oxidation and reduction, and that reduction is actually the opposite of oxidation. So, if you know one, then the opposite is the other. So let's take a look at the different types of definition. Oxidation can be defined as the gain of oxygen. For example, if I have this kind of equation and the magnesium has changed to magnesium oxide, that means that the magnesium has gained oxygen, and we say that the magnesium has been oxidized. The opposite would apply to reduction. So if copper oxide changes to copper, for example, that means it has lost oxygen, and that is reduction. In some reactions, we don't have gain or loss of oxygen. We could be talking about transfer of electrons. So you should realize that oxidation is loss of electrons. That means if I have something like sodium that has one electron in its outermost shell and it loses it and becomes Na+, that is an oxidation reaction. Now the opposite would be reduction. If I have something that gains one electron, for example, like chlorine, and becomes Cl-, this means that the chlorine has been reduced, and this is a reduction reaction. It could also involve loss or gain of hydrogen. So oxidation will also be regarded as loss of hydrogen if something like this in organic chemistry, if this is ethene changes to ethene, this is regarded as an oxidation reaction. Reduction would be the opposite. So here nitrogen gained hydrogen, the gain of hydrogen is reduction. Now, another definition involves oxidation number. Now, oxidation is the increase in oxidation number. You should know that oxidation number is actually the charge on the atom. So if I have iron 2 or Fe2 plus, we say that its oxidation number is +2. If that changes to iron 3, that is Fe3 plus, that means that the charge has increased from +2 to +3, that is oxidation. The opposite would happen if we're talking about reduction. The oxidation number decreases. So if I have Na plus, we say the oxidation number is +1. Now, Na without any plus or minus on it, we say that the oxidation number is 0. So Na plus to Na has changed from +1 to 0. That means the oxidation number decreased. This is called reduction. Of course, you should realize that that involves gain of electrons also. When Na plus changes to Na, it's actually gaining an electron. So that is reduction. Or if iron 3 changes to iron 2, that is also reduction. Now, a redox reaction is one that involves both oxidation and reduction. For example, this first equation, now what is happening? The copper oxide has changed to copper. That means the copper oxide has lost oxygen. Loss of oxygen is reduction. Now, the hydrogen, what happened to the hydrogen? It changed to H2O. That means it has gained oxygen. So we say that the hydrogen has been oxidized. Second equation, the Fe has changed to Fe2 plus. If we say with respect to transfer of electrons, well, that means that the Fe has lost electrons, and that is oxidation. If we say with respect to the oxidation number, well, the Fe has no charge on it, so the oxidation number is 0. It changed to Fe2 plus, that means it changed from 0 to +2. That is an increase in the oxidation number, that is oxidation. And we say that it is the Fe that has been oxidized. Now, copper 2 plus has changed to copper. That means either you say that it has gained electrons, or you say that the oxidation number has changed from +2 to 0. That means the oxidation number has decreased, and that is reduction. So a typical question would be something like this. Explain why this reaction is a redox reaction. We said, what's a redox reaction? It's one in which we have oxidation and reduction. So you have to tell me, where has oxidation happened, where has reduction happened? of course, the zinc to zinc 2 plus, that means that the zinc has lost electrons or it has increased in oxidation number, so the zinc has been oxidized. The copper 2 plus has changed to copper, that means it has gained electrons or the oxidation number has decreased, so this is the one that has been oxidized. Now, when something is oxidized or reduced, then there is something called an oxidizing agent and a reducing agent. So when a substance is reduced, it is the oxidizing agent, because when it is reduced, that means it gives its oxygen to the other one. So it is the oxidizing agent. So if we're looking for which one is the oxidizing agent, it is the reactant that has given oxygen or that has been reduced. In the lab or in experiments, if he says suggest the name of an oxidizing agent, remember that potassium manganate is an oxidizing agent, potassium dichromate is an oxidizing agent, halogens are oxidizing agents. You also have to remember that potassium manganate is something that changes from purple to colorless when it reacts. So if he tells me that compound A reacted with potassium manganate and changed it from purple to colorless, potassium manganate is an oxidizing agent. That means that the other compound is a reducing agent. Potassium dichromate is something that is orange in color. When it reacts with a reducing agent, it changes to green. Reducing agent, again, the reducing agent is the one that has been oxidized, or it is the one that gains the oxygen. That means it causes the other one to be reduced, so it is the reducing agent. If it says suggest examples of reducing agents in a lab, when we want to do a reaction in which we need a reducing agent, then we react that substance with hydrogen or with carbon, in the form, usually in the form of coke, or with carbon monoxide or metals. Because metals lose electrons, they become oxidized. The other substance that they're losing electrons to become reduced, so they act as reducing agents. So in this question again, remember we said that the copper oxide has been reduced, the hydrogen has been oxidized. So which one is the oxidizing agent and which one is the reducing agent? We said the one that has been reduced is the oxidizing agent. The one that has been oxidized is the reducing agent. Remember when he says which one is oxidizing agent, which one is reducing agent, we're looking at the reactants, not the products. So don't tell me the copper is an oxidizing agent or the water is an oxidizing agent. You're looking at the reactants. The second equation, remember we said from Fe to Fe2 plus, that is oxidation. That means the iron has been oxidized. That means that the iron is the reducing agent. The copper 2 plus has been reduced. That means the copper 2 plus is the oxidizing agent. Okay, so that is with respect to types of reactions with respect to oxidation reduction. The next type of reaction that we'll talk about is reversible reaction. Reversible reactions are reactions that go both forward and backward without going to completion. What does that mean? Now, most reactions just reactants A plus B gives C plus D, and that's the end of it. So all the reactants change to products, so we say that the reaction goes to completion. But some reactions are reversible. Reversible means the reactants react to form products. And then the products break down to form reactants again, and then the reactants react again to form products, and so on, and they keep going forward and backward. So we call that a reversible reaction. For example, if I have a container that has nitrogen and hydrogen gases, the nitrogen and hydrogen will react to give ammonia. But then some of this ammonia will break up again to give nitrogen and hydrogen. And then the nitrogen and hydrogen will react again to give ammonia, and so on. So we put this sign in the middle between them. Instead of an arrow going forward, it's an arrow going forward and backward, and that indicates that the reaction is a reversible reaction. So another example of a reversible reaction is this. If we have hydrated copper sulfate, you should realize that the word hydrated means it has water of crystallization, or the crystals have water in them. So instead of just being CuSO4, it's CuSO4 with 5 water in it. So that is called hydrated copper sulfate, and that is blue. Now, if I heat this blue solid, the water evaporates and it becomes anhydrous copper sulfate. Now, the anhydrous copper sulfate is white. If I add water to this white solid, it goes back and becomes blue because it becomes hydrated. You heat the blue hydrated, it becomes anhydrous. So this is another example of a reversible reaction. Also, if I have ammonium chloride is a white solid. If you heat it, it changes into ammonia and HCl. But remember, when we were talking about acids and bases, we said ammonia is a base, it reacts with HCl, which is an acid, and it goes back and becomes ammonium chloride. So you get the white solid again at the top of the test tube. So again, this is an example of a reversible reaction. Now, the reaction will keep going forward and backward until what? Until it reaches what we call dynamic equilibrium. Now, when it reaches dynamic equilibrium, the rate of the forward reaction equals the rate of the backward reaction, and concentrations of reactants and products remain constant. That means we look at the reaction, it appears that it's not doing anything, but actually it is going forward and backward at equal rates, and the concentrations of reactants and products do not change. For example, if I have this reaction, nitrogen dioxide gas is a brown gas. Now, sometimes it dimerizes, that means every two join together and form N2O4, which is a colorless gas. But this colorless gas can again break down to form a brown gas. Now, if we see this in the test tube, the nitrogen dioxide gas is brown, it changes to colorless, and then the colorless changes to brown, and so on, until they reach dynamic equilibrium. Now, dynamic equilibrium is that test tube in the middle where we're in between all of this, and the reaction is going forward and backward at the same rate, so you don't see any change, but actually it is reacting, and that is what we call dynamic equilibrium. Okay, usually when we have a reversible reaction, we do not want it to keep going forward and backward. We need to change it because we need, for example, in this reaction, I want to prepare ammonia. I don't want the ammonia to break down again to go to nitrogen and hydrogen. I want the ammonia to get forward, the reaction to go forward, so that I get as much ammonia as possible. So what can I do to the reaction in order to force it to go either forward or backward, or force it to go to the right or to the left? That means I'm affecting its point of equilibrium. So at equilibrium, the forward is the same as the backward. The rate of forward reaction is equal to rate of backward reaction. Now, I want the forward to be faster, or I want to go more forward than backward. That means I'm trying to affect the point of equilibrium. Okay, what can I do to the reaction to force it to go forward? For example, the first thing I could do is I could change the pressure. But remember that changing the pressure applies only if we have gases. So if I have a solid or a liquid in this reaction, I cannot say increase pressure or decrease pressure. Okay, so if I have gases, I can change the pressure. What should I do to the pressure to force a reaction to go to one side rather than the other? If I increase the pressure of a reaction made up of gases, that means you're pressing the molecules nearer to each other. That means you're making them more crowded. They would want to go to the side that will make them less crowded. That means that increasing the pressure in any reversible reaction will cause it to go to the side that has less number of molecules. Now, which side here has less number of molecules? You should see that the coefficients or the numbers before each compound is a ratio of the number of moles or a ratio of the number of molecules. So, if we go forward here, we form 2 molecules of ammonia. Now, if we go backward, we're going to form 1 molecule of nitrogen and 3 molecules of hydrogen. That means I'll be forming a total of 4 molecules. And we said if we increase the pressure of any reversible reaction, the reaction will go to the side with less number of molecules. So in this case, if I increase the pressure, then the reaction will go more forward. So if he says we're increasing the pressure, what is the effect on the point of equilibrium? You will tell me the reaction shifts to the right or it goes forward. If he says, what is the effect on the yield of ammonia? What do we mean by yield? Yield means the amount of ammonia I'm going to get. Well, if it's going to go forward, that means it's going to give me more ammonia. So the yield of ammonia increases. Please pay attention to which question he's asking. Again, another condition I can change is the temperature. Okay, what happens if I increase the temperature of any reversible reaction? Well, we said if we're increasing the pressure, we look at which side has less molecules. But if we're increasing the temperature, then we look at which side is exothermic and which side is endothermic. Do you remember that? We said exothermic reactions are reactions that give out heat and their delta H is negative. So can you see that delta H at the end of the equation? He's telling me that delta H is negative, or he would say that delta H is minus something. That means going forward, nitrogen plus hydrogen to give ammonia, the reaction is exothermic. That means that the temperature of the reaction rises. Now, I want it to go forward. Should I heat it or cool it? Well, what I do to the reversible reaction, it will do the opposite because it wants to remain at a certain level of temperature and concentration and so on. Now, remember that if we increase the temperature of any reversible reaction, that means you are heating it, it will try to cool itself. So it will go to the side that is endothermic. Increasing the temperature, the reversible reaction goes endothermic. Now, if this reaction in front of me is saying that the forward is exo, that means that the backward is endo. So that means that in this reaction, if I increase the temperature, it will go backward. Or we say that the point of equilibrium shifts to the left. So if he says he increased the temperature, what is the effect on the point of equilibrium? It shifts to the left, or the reaction goes backward. Now, if I say what is the effect on the yield of ammonia? Of course, if the reaction is going to go backward, that means the ammonia is breaking up to form nitrogen and hydrogen. That means the yield of ammonia will decrease. I will get less ammonia. Okay, something else that I can change would be the concentration of the reactants and the products. So if I add more reactants, the reaction will try to go forward in order to use up these extra reactants. If I add more nitrogen, it will go forward and give me more ammonia. If I remove the products, if I remove ammonia as it is made, we remove it. As it is made, we remove it. That means we're decreasing its concentration. It will try to go forward in order to go back to its original concentration. So, adding reactants in any reversible reaction or removing the product causes the reaction to go forward. That means the point of equilibrium will shift to the right and we will have a higher yield of the product. Okay, so the other factor that we can change is catalyst. We can add a catalyst to the reaction. You should realize that a catalyst is a substance that speeds up a reaction. Now, if we add it to a reversible reaction, it will speed up the forward and the backward. So that means it has no effect on the point of equilibrium. It doesn't force the reaction to go forward or to go backward. It just increases the rate of both. That means that the reaction reaches equilibrium faster, but there is no effect on the point of equilibrium. Okay, thank you for listening. This was a video on redox reactions and reversible reactions. Please keep listening to the videos. Thank you.